In this video I want to talk about 1-bit adders. So let's say we have 2 bits A and B and we want to find the result of adding the two. So we know that if we have 0 plus 0, and remember these two are binary numbers, so the result is going to be 0. If we have 0 plus 1, the result is going to be 1. The same is true for 1 plus 0, which will be 1. And finally, if we have 1 plus 1, the result is going to be 1, 0 in binary. So these are all in base 2. So that means that if we want to find the Boolean equation for a circuit that implements this functionality for us, we basically have to go over all the possible combinations. So for these results, what we can do is that since the result of 1 plus 1 is 1, 0, what we can do is that we can divide the result into 2 bits. So the first bit, or the least significant bit, we call it as the result of the summation, and the second one we call it as the carry out that is being created. So as you can see, the carry out is 0 for 3 out of the 4 cases, and it is only 1 for when we add 1 plus 1. So let's just fill out the truth table that we have for this half adder unit. And I will explain more why we call this half adder. So when we have A and B both being 0, the cout is 0, and the result of summation is also 0. When A is 0, B is 1, cout is again 0, but the result of summation is now 1. The same is true for the next row as well, when A is 1 and B is 0. So carry out is 0, and the result of summation is 1. And finally, when A and B are both 1, we have a carry out, and the result of summation you can say is 0. So if you want to write down the Boolean equations for these two functions, we have several different techniques to use. So the easiest one is the sum of product. So let's say for the result of summation, or S, all we need to do is that we need to OR the mean term for which the output is 1. So S becomes A bar B or A B bar. And as you know, this is basically A XOR B. As for the cout, there is only one mean term, or one row for which the output is 1. So this is simply A B. So this is what we call as the functions for a half adder. So why do I say a half adder? So as you can see here, we found the result of adding only 2 bits. But what if we have 2 variables, each having 4 bits? So let's just call this K, and let's just call this L. So if you find the value for summation of the first 2 bits, or the least significant bit, what we basically have is bit 0 here for the first value and bit 0 for the second value, and we basically do the summation. We end up with a summation result, and we have a carry out. Let's just put the 0 as a superscript. So as you can see, we only finding the result of addition of 2 bits, right? Since this is the least significant bit, there is no carry from the previous state. But what if we want to find the result of summation for these 2 bits, so K2 and L2? So in this case, not only we have to consider K2 and L2, but we might have a carry from the previous stage as well. And then we have a carry that goes to the next state. So the reason that this is called a half adder is that because it only considers the carry out and it doesn't consider having any carry in from the previous stage. So let's just modify this design, and now instead of only having bits A and B, we have a carry in from a previous stage too. So in this case, we have 8 possible combinations because we have 3 inputs, but the result or the way that we calculate is exactly the same. So C in plus A plus B, when they are all 0, create a carry of 0, and the result of summation is again 0. When C in is 0, A is 0, B is 1, carry out is 0, summation is 1. Similarly, when carry in is 0, A is 1, B is 0, carry out is 0, and summation is again 1. When carry in is 0, A and B are both 1, we have a carry out as 1, and the summation is going to be 0. For the next row, we have only a carry in, but the 2 bits that we want to add, they are both 0, so that makes the carry out in this stage to be 0, while the summation is 1. For the next one, we have a carry from a previous stage. A is 0, B is 1, so carry out is 1, summation is 0. For the next row, we have carry in from a previous stage. One of the bits is 1, the other one is 0, so we have 1 for the carry out and 0 for the result of summation. And finally, when we have all of these inputs, carry in A and B, to be 1, we have a carry out, and the result of summation is also 1, because 1 plus 1 plus 1, it is going to be 3 in decimal, which is equivalent to 1 1 in binary. So now let's say we want to find the Boolean equation for these two variables, C out and S. Again, it is very straightforward and easy. We can use sum of product. So if I want to write the equation for S, I'll be looking for rows for which the output is 1, and I just write down the associated min term and OR them together. So it's going to be C in bar A bar B plus C in bar A B bar plus C in A bar B bar plus C in A B. This is equivalent to XORing these 3 inputs as well. So this is C in being XORed with A, being XORed with B. We can do the same for C out as well and use the sum of product form to come up with the Boolean function. So it's going to be C in bar AB plus C in A bar B plus C in A B bar, and then finally C in A and B. And as you can see here, we can simplify this equation as well. So for example, between this one and this one, C in A is common, so we can factor it out. Or between this one and this one, C in B is common, so we can factor it out. In fact, you can use a Carnot map representation to find out the most simplified version of the function. So if we do that, the final function that we get for calculating the carry out for a full adder is going to be AB plus AC in plus BC in. So as you can see, the half adder is only being used when you want to find the result of summation for the least significant bits, and only that one. So when you want to find the result of summation, let's say this one is variable A, this one variable B. So if we call this A0, we call this B0. So the result of summation for A0 plus B0 can be calculated by a half adder because we don't have any carry in from a previous state. But for all of the other bits, we need to use a full adder. But you might say, okay, we can still use a full adder for calculating the result of summation of A0 and B0 too. All I need to do is that for this stage, I need to make the Cin to be 0. And you would be right. So this is how we can create individual units for adding 2 bits. In later videos, you will see how we can combine them to create multi-bit adders.